So this was a very interesting talk. And up next, we have a next talk with a very interesting title called Betterer Incremental Improvements by Craig Spence. So the Craig is a software engineer originally from New Zealand, currently working at the Spotify Stockholm. Besides that, he's an Angular GDE. He loves building cool things that help teams build cool things, which sounds like a buildception. Let's see what he has to say about that. And besides that, he also loves punk rock, Disney's Frozen, and his cat Cozy. So please, everyone, let's welcome Craig. I have to say, I really like this intro song, like in the Angularday, it's like just starts to vibe with it. But hey,
Yeah,
Craig,
it's great. It's a good
welcome.
vibe. How you doing?
How are you doing?
I'm great. How are you?
Oh, very, very nice, very good. So I would like to ask, like, is there any chance that we are going to see your cat today, maybe as a guest speaker somewhere in the background, maybe on the couch?
Unfortunately, that cat is not in Sweden. So
All right.
yeah, no.
So is it the southern or the northern island where you are from originally?
The North Island of New Zealand.
All right. It's a
A
very
little place
beautiful
called
place. And
Whanganui.
before we start, maybe you can expand our horizon and tell us what is like your top one best punk rock band of all time. Hard choice.
So hard.
You have to pick one.
If I have to pick one, at the moment I'm on a bit of a propaganda kick. They're a Canadian hardcore band. Been around for a long time.
I have to definitely check that one out. It's
they're all
always like best
vegan.
to
They're
get the
all
real
very
tips from the
angry.
people, right? Anyway, so let's not delay any further and jump straight into the talk. Let's go.
This is the sun. The sun is a massive ball of burning hydrogen. It's a fusion reactor that pumps heat and light and radiation out into the solar system. It keeps Earth alive and it keeps us alive. And over the next 5 billion years or so, it's going to run out of hydrogen fuel and start burning helium, at which point it's going to grow and grow and grow and eventually turn into a red giant. Over the next several billion years after that, it will grow so large that it will eventually engulf Mercury and then Venus, and then most likely it will consume the Earth. Incremental growth can have a really big impact over a long period of time. Tiny little changes, tiny fractions of a percentage of growth each year will add up over billions and billions of years and eventually destroy the entire planet that we call home. It's simultaneously incredible and also kind of terrifying to think about. Now, I don't know about you, but frankly, there's been enough scary stuff going on in the world for the last little while, and I'm kind of overwhelmed by it all. So instead of thinking about this, we're going to chill out for a little bit and we're going to talk about computers. But first, a little bit about me. So hi, that's my face. This is my face. My name's Craig. And much like the sun, I'm a super hot giant ball of existential terror. I'm from a small town called Whanganui in Aotearoa, New Zealand. But right now I live in Stockholm in Sweden. And like many of you, I have the privilege of writing software to earn my keep. My day job is working on the desktop app and the web player at Spotify. But outside of that, I'm also a Google developer expert for Angular. And I really love the web. I really love helping teams build better software. I'm very much online, so feel free to jump on any of these things, reach out to me, get in touch. Also, if you want and you've got time, you can scan this QR code and get these slides and just follow along on your screen if you want. So over my career, I've so far worked on a number of quite large and quite old code bases. And though, of course, large and old are relative terms. I've been also lucky enough to work in environments that kind of espouse the core ideals of agile software development, trying to push for incremental change and always trying to be shipping working software. I've worked with systems that are capable of pretty incredible experimentation to really understand the impact of product changes and get a lot of user feedback. But even with all that information, I've been involved in multiple big confrontational user interface rollouts where there was no real going back. So no matter how much you think it's the right thing to do, incremental change is really hard. But perhaps more specifically, dealing with legacy software is hard. A legacy code base is also a victim of incremental change over a long time because code bases naturally evolve throughout their lifetimes. Priorities change, teams change, technologies change. But a mature system is quite a powerful thing. And there are significant benefits to like maintaining a status quo. You shouldn't underestimate the value of stable working software that has had years of real users, years of bug fixes, years of engineering time invested. Billion-dollar companies often exist on this type of code, an original prototype that became productionized or some big monolith that people have tried and failed to break apart. Legacy systems are often quite stable and they can happily keep running along until you try to change it, and then everything breaks. And if it's hard to change your system, that means it's hard to fix bugs and hard to deliver new value to users. And so often you come to a point where a system is not actually stable, but it's more in a gradual state of decay. You can kind of ask yourself what a system might look like in 6 months or a year or 5 or 10 years even. Sometimes a codebase can end up in a state where it cannot be safely changed without making something worse. You've optimized for some current situation and reach what is known as a local maximum. A coworker once referred to a codebase as being in a state of accidental immutability. No matter what we did, something broke. There wasn't a safe path from where we were to where we wanted to be. Now, most of us have some ideas of what we want our codebase to be like. We can imagine some amazing utopian state that exists, but it might seem entirely out of reach. You could be limited by time or money, anything. Your team has got a current set of priorities and you've got to keep shipping stuff, so changes have to happen and they happen more dangerously. It gets harder and harder to make changes, your velocity slows down, and eventually what used to be an engineering problem is now an everyone problem. Everyone wants to find a way to get back to delivering value to the users, and maybe eventually someone says, why don't we rewrite the whole thing? And rewrites are kind of exciting. It's like a revolution. Everyone gets to try out bold new ideas, everything happening really quickly, making lots of progress, unencumbered by the shackles of the way you used to do things. You can move fast and break everyone's stuff and build newer, better, shinier things. And sometimes revolutions are necessary. Sometimes a system is so broken that the best way through is to burn it all down and start again. And hopefully you do end up with something better. But they can also be super dangerous, and a lot of people can get caught up in the middle of you tearing apart the status quo. With software particularly, there are many cautionary tales of revolutionary change where it's all gone wrong. We always think it'll be different from us. In my experience, it inevitably involves scope creep, too many things changing at once. There might be like a full redesign and changing your tech stack and introducing new workflows and new coding standards and so on and so on. You may end up through the other side, but there's always a cost. Best case scenario is that's just time and money, but I've seen full rewrites have a significant impact on people as well. At a minimum, if you're not careful, really important knowledge can be lost. Tiny implementation details for weird edge cases, or important business critical unit tests or other tests, or even just years of context from comments in version control history. So are there any other options other than a full-on burn it all down revolution? There's another viewpoint that says that the best way to change a system is from within the existing system. So instead of suggesting a full rewrite, it might be better to attempt to make things better within the existing code base and take on the pain of that local maximum. You can start a new branch and start working away on a fix. This is the tried and true approach for smaller changes, obviously, but what about for huge bits of technical debt? Some pieces of technical debt are so coupled to the rest of the code that you can't really fix it piece by piece. Often technical debt is so compounded that it's hard to find time to pay it all off at once. And technical debt can also be really hard to quantify and therefore hard to prioritize. So you might have this tech debt branch, and it might exist for a long time, slowly being worked on where it's possible. But the branch diverges away from the main code base, and merging gets harder and harder. Along with the technical challenge of keeping things up to date, there's also now a communication problem, because other contributors continue to do things in the old way off the main branch. One way to try to communicate this new plan to the rest of your team might be to add a lint rule to the main branch so that people don't add new issues. But what should you do with potentially hundreds in a large code base existing errors? Option number one is often to add comments to just disable the lint rule all over the place. But in my experience, what that does is just make it look like that's okay. Existing code can get copied and pasted around, and so more and more disabling comments just show up. Option number two with the lint rule is just to make it be a warning. But again, in my experience, unless it breaks the build, no one really pays attention. Either way, people continue to do things the old way, and the decay continues. Sometimes it's possible to completely automate a change, which can really reduce the pain of that communication breakdown. People might still do things in the old way, but that doesn't matter because you can automatically migrate their changes to the new way. And we already use a lot of automation to do big improvements in our code base. We might use a tool like Labab to migrate from old JavaScript to new JavaScript, or an Angular schematic to upgrade to a latest version of Angular, or a tool like Prettier to make our code formatting consistent, or even a custom lint rule with a fixer that's going to fix some specific issues in your code. Some things can't be automated completely, but often you can get 90% of the way with an automated script and then tidy up the last little issues manually. There are, of course, a large number of problems that computers can't solve yet. Humans are currently still the winners when it comes to more creative or subjective endeavors. While a computer can easily find all uses of an old deprecated API, it can't necessarily tell which of the new shiny APIs it should use to replace them. Let's look at an example. Let's think about buttons for a second. Pretty much every application has them, and lots of them. It's not uncommon for them to be implemented something like this, where different classes are used to change the color. And this is totally fine. It works pretty well. But unfortunately, it starts to fall apart a little bit when you start thinking about changing the whole theme of your application. Say you're going to introduce a dark mode. Instead of describing your buttons by what color they are, you might actually want to describe your buttons by the semantic function of the button, what the button does, not how it looks. You might change your buttons, change the classes, to be something like this. I've worked with multiple design systems that have gone through this exact migration, and maybe you've seen it too. The challenge here is that there isn't a direct one-to-one mapping from color to semantic meaning, so it can't really be automated. In the worst case, you might need to go through every single button and decide how to migrate it. Chances are you might even have a messy in-between state where you have multiple different button implementations in your code base, lint rules, deprecation notices, the whole lot. And it will take quite a concerted effort to actually make the migration happen. So how would we approach this? Let's think about how a human would migrate all these buttons. Say you have 100 buttons. You'd find the first button and perhaps you work with a designer to apply some rules to decide what sort of button it should be. Does it designate a positive action or a destructive action or something else? You'd update the code for that specific button to apply the semantic meaning, and now you're 1% done. Only 99 more to go. Pretty straightforward, right? The hard part here is what applying some rules means. It's another communication problem. You need to be able to specify the exact justification for why a button might have one semantic meaning over another. This kind of nuance is hard enough to express to another human, let alone a computer. So how do we break down these rules? How do we express this kind of imperfect, heuristic-based decision to better communicate what we're trying to achieve? What it ultimately comes down to is that Humans are actually pretty good at breaking down problems. If you break down a big problem into a set of smaller problems, this can be easier to solve individually. You might have some problems combining those small solutions, but that's just another problem which we can then break down and solve. And there's been a continuous movement towards building software in this way too. Microservice architectures have become popular rather than big monolithic applications. Each part of a system can be considered separately and can be changed separately without impacting the whole. This is similar to component architectures in Angular code, where smaller components are easier to reason about and change. These architectures put a large emphasis on how each of the smaller parts communicate with each other, so that as long as you don't break the contract or the API, the implementation can change however it needs to, independent from other components. Of course, this kind of architecture doesn't come without cost, and you might introduce new problems to do with ownership and composition and how to deal with poorly designed APIs. But the fact remains that building systems in this way allows for change to happen in smaller chunks and for the system to evolve over time. Actually, it turns out there's a whole category of algorithms for finding solutions via these kind of evolutionary processes. An evolutionary algorithm is an algorithm that explores possible solutions using a heuristic that is inspired by natural evolution. These algorithms reflect the process of natural selection, where the fittest individuals in a population are most likely to successfully reproduce in order to produce offspring of the next generation. One specific type of evolutionary algorithm is called a genetic algorithm. A genetic algorithm has two key inputs. The first input is a genetic representation of potential solutions to the problem. Each variable in the solution is called a gene, and a group of genes are combined into a chromosome, which represents one solution to a problem. A number of potential solutions are collected together as a population. To solve a problem with a genetic algorithm, the implementer has to decompose the problem into all the variables that might impact the solution in order to figure out which each gene should be. This is analogous to how we might try to come up with a description for our rationale behind picking a success button over a danger button. The second input is a fitness function, which takes a chromosome from the population as an input and evaluates the fitness score of the solution. Each chromosome in the population is evaluated by the fitness function so that each chromosome has a fitness score. Once the fitness score of the whole population has been evaluated, the selection phase begins. First, the solutions are sorted by their fitness order, and some number of weak or low scoring solutions are terminated. Next, a crossover phase begins and selects the number of genes to be shared between two parent chromosomes. Then, pairs of chromosomes combine to make new chromosomes until the population is back to its original size. Finally, some small number of genes within the new chromosomes are mutated. Then the fitness phase starts again, and each member of the new population gets a fitness score. Then the same selection process happens again, and this continues for many generations and should eventually tend towards a good, but not necessarily optimal solution to the problem. It's entirely possible for a genetic algorithm to end up at a local maximum. So let's explore how we might decompose a problem that can be used with a genetic algorithm by thinking about the game Tetris. When we play a game of Tetris, our brains are applying a set of rules for whatever we might think is the optimum strategy for getting a high score. We might try to consistently clear lines wherever possible, or try to save up lines so that we can clear forward a time. But we have to decide how we place the tetrimino pieces in order to clear lines. Perhaps we want to have as many sides of the current block touching the bottom as possible, or as many sides of the current block touching another block. Maybe we should just try to avoid introducing holes between our bricks. Each of these variables for playing the game can be a gene in a chromosome that describes a solution. The fitness function for Tetris is just playing the game with the given genes and seeing what score you get. Here's an example where I've implemented exactly those rules into a genetic algorithm that learns to play Tetris. Each chromosome contains 10 genes, where each gene is a variable that impacts the strategy for playing Tetris. The initial population has random values for each of the genes. The fitness function simply plays the game with those given weightings for the chromosomes, and then the chromosomes are compared by their final points total. At first, they really suck at playing Tetris, but over a series of generations, the chromosomes become better and better, very quickly becoming much better than me. By decomposing the problem like this, we can describe the game of Tetris in a way that allows for incremental improvement over time. Wouldn't it be great to have a way to describe a change you want to make in your codebase and define what incremental progress towards that final state looks like? We know what a codebase looks like now, and we know what we want it to look like. So we just need a way to break down the difference between those two states into smaller pieces that can be dealt with incrementally. We also need a way to break down our codebase into quantifiable, countable pieces, much like the chromosome in a genetic algorithm. We need a fitness function that evaluates the solution and gives us some kind of score for our codebase. It actually turns out that there are many ways to represent our codebase. First, we just need to think about our code as data. Let's look at this little bit of code. What different kinds of data can we get from it? First, there's the actual code that runs the program. From this, we can determine that this function is asynchronous, it has one argument, and that it contains a call to a constructor. But then there's also the documentation and the comments as well, which could contain information at a higher level than actual code. There's also dependency information, like how our files relate to each other and how they use third-party dependencies. Then there's also type information about how data flows through the program. We can use various tools to read our codebase and quantify it in all kinds of different ways. We could count the number of files with a certain extension, or the number of circular dependencies, or the number of compiler errors. By quantifying these things, we can break the program down from one big thing that needs fixing into individual small things that can be fixed independently. But that's absolutely nothing new, right? It's a slightly different way of thinking about it, but that's what TypeScript or ESLint or Jest or Axe or any other number of tools already do. We can think of TypeScript as a fitness function that transforms our codebase from code into a number of compiler errors. What we need is a way to compare the state of the codebase between two different points in time. So let's say we start with our main branch and run the fitness function over the codebase to get a representation of the current state of the code. We have some work done in another branch which also contains the code, which changes the codebase in some way. We can run the fitness function again on the new branch to get the new state of the code. We then need to define a comparison function to assess the difference between the two states. The comparison function has the job of working out if the new state is better than the old state, if it's worse than the old state, or if it's the same as the old state. The comparison function will act as a constraint, guiding your codebase in the right direction towards being better. This means that the result of the fitness function can actually be anything you like, as long as you can compare the results. But changing branches all the time to evaluate this fitness is kind of tedious. So is there a better way to keep track of the current state of the main branch? It's become pretty common to store extra information about a codebase in the repository. Chances are that somewhere in your codebase you've got a dependency lock file, or maybe a Jest snapshot file, or even an actual image file somewhere for visual regression testing. We can use the same idea and store the current quantified state of the codebase inside the codebase. This adds one extra constraint to the result of the fitness function. It needs to be serializable so you can save it in a file, but that means that we can always compare the current state to the last committed state. And so with that, we have the three little bits we need to enable a gradual incremental migration in a situation where automation isn't feasible. We need a fitness function that takes our codebase and turns it into a quantified, serializable representation of the codebase. We need a comparison function that takes two representations and determines if one is better than the other, or worse than the other, or the same as the other. And we need a mechanism for writing results to disk so they can be stored in source control and compared between branches, kind of like a Jest snapshot file. I've been working on wrapping this idea up in a little tool. I've been calling it Betterer. Betterer is a tool designed to make incremental improvement easier. You can think of Betterer kind of like a test runner, like Jest or Mocha. The difference is that Betterer starts out as broken by default. A Betterer test is a way to communicate your intentions to other developers, that there is something that you want to improve in the codebase, without the need for disabled lint rules or long-lived branches, and without needing to burn everything down to start again. You can check out the docs online or just run the initialization script in a project to get started. Let's dive in and see how it works. We can run the initialization script with npx to set up Betterer in a codebase. When we run that script, it adds a new script for us to run Betterer and also adds some dependencies and stuff like that. The initialization script also creates a new Betterer config file, which contains the entry point to your test. It's TypeScript by default, but you can use JavaScript if you prefer that. And straight out of the box, it's actually enough for Betterer to start doing its thing. Of course, right now it actually does nothing since we haven't defined any tests. But let's fix that. So, what should a test do? The test is a fitness function for our codebase, and it can be basically anything that you want, as long as you can represent the result in a way that can be compared. As an example, I have a project that I want to convert from JavaScript to TypeScript. So let's write a test that counts the number of JavaScript files in a codebase. First, we go into our betterer.ts file, and we import Betterer test from Betterer. And then we're going to define a new test called migrate.js to TS. Next, we need to write our actual test function. This is the function that scores the fitness of the codebase. For now, we're simply going to use the glob library to count up the number of files with the JS extension. A number is nice and easy to compare, and it's also serializable, so that's good. Next, we need our constraint function, which does the comparison between results. We're going to pull in Betterer constraint result and return better if the new result is smaller than the expected result, same if they're the same, or worse if the new result is bigger. In other words, if we have fewer JavaScript files, the test got better. If we have more JavaScript files, the test got worse. And if we have the same number of JavaScript files, our test has stayed the same. Comparing numbers like this is actually such a common use case that you can just import smaller from Betterer constraints. You might also use bigger for some tests. Now, if we run Betterer again, we're going to see something more interesting. We can see that our test migrate.js to TS got checked for the first time. Good job, us. So what did this do since we had nothing to compare it against? Since we didn't have an existing result to compare against, Betterer just runs the test and takes what it gets as the base state. It serializes the result and stores it in a new file called Betterer results. This is simply saying that there are currently 9 JavaScript files in this example codebase. And this is a file that is basically the same as the Jest snapshot file. Now we can run Betterer again, and this time we'll see that our result is the same. We didn't change anything in our codebase, but Betterer found the results file and used that as a comparison point. This is fine. Nothing got worse, so we haven't gone backwards. And that's that. We've almost got our first test working. So we've got everything set up, and along comes our friendly neighborhood engineering manager, and they're adding a new feature, and they haven't yet heard about the new plan to migrate to TypeScript. They add a new JavaScript file to the project, and when they try to commit, they get a big error, and they can't move forward. That's good for the state of our code base, but it maybe doesn't quite communicate what's going on as well as it could. Let's change a few things to communicate more clearly. While our initial approach was fine, it's actually pretty common to want to have a test that targets specific file types in your code base. Betterer gives us a really easy way to do stuff like that by using a file test. Let's try that out. The way that you create a file test is a little bit different. It just takes a function with two parameters, file paths and file test result. Betterer can be quite smart and sometimes will only pass you a subset of file paths. There's a watch mode you can run in, for example, or if it knows that a given file hasn't changed since the last time Betterer was run. The file test result is an object that we use to tell Betterer about issues in a file. Here we're going to use the include method to tell Betterer that we only care about JavaScript files. And Betterer will automatically exclude any files that are excluded from source control. The body of the test is actually pretty simple. Since the test only targets JavaScript files, we just need to create an issue for each file passed to the test. To do that, we need to read the file contents using fs, and then call add file on the file test result object. We then call add issue on the file, and we pass it the position of the issue. Using 0 and 1 is simply going to attach the issue to the first character of the file, and we also give it a nice helpful error message. So that's tons better. If we run Betterer again, there's much more detail about what's gone wrong, and we get a nice little code snippet in the error message. Because we use a Betterer file test, there are still 9 files found with the issues, but there's actually a lot more detail in the results file. When Betterer serializes the results of the file test, it includes some information about where the issues are located in your codebase. This is so Betterer can track issues if they move around within a file or if a file is renamed. With the results file updated, we can commit and merge our updated tests, and our EM can update its branch. As an extra bonus, and for even faster feedback, we can get our engineering manager to install the Betterer VS Code extension so they can get nice errors in their editor when they make changes. Now, because our friendly EM only actually gets like 15 minutes to code a week, they don't actually have time to fix the JavaScript right now. That's okay. They can just use the update flag to force Betterer to update the results file, just like with just snapshots. This means that they can move on and make a PR. Because the results file is committed with the code, hopefully someone will pick it up in a code review and challenge them on that decision. But sometimes you just have to make things a little bit worse so you can move forward. But really, it should be a last result. In this case, it forces Betterer to update the results file, and now we can see that there are 10 total issues instead of 9 we had before. So now that the results file matches the state of the code base, Betterer will go back to reporting to the testers the same, and now we're back to having stable code. So even though they couldn't help out this time, our friendly engineering manager really loves this idea, and they know that we have to get this migration finished. Our team can discuss an appropriate date by when they want to meet their goal, and they can set a deadline for this test. Once the expiration date is passed, the Betterer reporter just gets a little bit more shouty about what's going on. So now the team has agreed to prioritize the migration, other team members can dedicate time to fixing up the issue. Someone on the team comes along and they migrate the new file that the engineering manager added, as well as one more for good measure. They run Betterer again, and it reports that 2 issues were fixed. Now we're even better than we were before. Since things got better, Betterer will overwrite the results file and cement in the new, healthier state of the codebase. If the JavaScript files are changed back or added again, Betterer will report that the test is worse again and the build will fail. So there are tons of different things that we can apply this idea to. Say we've got a TypeScript project or an Angular application where strict mode hasn't been enabled. We could use Betterer to enable more strict compilation throughout our code base. We could use ESLint or StyleLint to introduce new rules to our code base, or even track out of control to-do comments using a simple regex test. It doesn't have to be front-end. We could even lint other languages like Kotlin or Swift. We could enable super strict template type checking in an Angular application, or check accessibility violations with Axe, or even check our code coverage with Jest. There's a ton of possibilities. As you can see, Betterer gives you a lot of potential power in how you define your tests and how you measure your test progress. But since tests are just functions, it's pretty easy to just wrap up this power and complexity into a module that can be shared or reused. Betterer comes with a few tests that are built in with to help you get started. I'm actually just about to release the Angular test, which is specifically designed for that use case of enabling strict template type checking. In my experience as a GDE, a lot of teams are really struggling to enable that. So hopefully this will be an easier way for people to turn on strict template checks. Okay, so that's Betterer. If you can't tell, I'm pretty excited by this idea. I've been working on it for more than a year, and I still haven't lost interest, which is a pretty good sign. If this is exciting to you as well and you'd like to join me, please hit me up. We're probably not going to stop Earth being swallowed by the sun, but we might be able to make some stuff just a little bit better. Thank you so much. It's so great to be able to spend this time with you, even though it's still online. Hopefully we can do it in person at some point. Feel free to reach out to me on Twitter or anything, and obviously super happy to take questions now if anyone has them.
Hey, Craig, thank you very much for a very interesting talk. And folks, really do not hesitate. Ask the questions either in the chat or in the Q&A panel. And we are going to relay them to the Craig so you can get your answers. And from my side, I would say like it was very cool and interesting to see like stuff which is very common to like front-end developers, like a TypeScript, ESLint, Prettier, or what have you. Like it's something which we are using on a day-to-day basis. But it was very interesting to see that from that first fresh perspective, like because most of us maybe heard about there is like some genetic evolutionary algorithms, but I never could make this kind of like connection that you can actually relate this kind of concept and look at it from that perspective. So that was very, very interesting.
Yeah, I think it's that there's some power in being able to break things down, and especially like, you know, when you run a new project and you get a list of 10,000 compile errors, it's just so overwhelming. And so being able to think about them one at a time is actually really useful.
Definitely. I mean, like one thing which comes to mind, like it's like a very cool concept, but let's say if we have like a larger organization which is having multiple projects, libraries, paths, what have you, is there some way currently to share like this kind of like better setup across the projects? Or is this something which is like on the roadmap, or what's the plan here?
Yeah, so it's all just JavaScript. So at any point you can wrap any of it up in a module and share that, and then just have one little config file in a project, and then import that. It's one of these interesting problems where you kind of only see it in big code bases.
Right.
You know,
But yeah, as you said, like basically folks can like get a set of like the preferred tests and configs, maybe put it in some dedicated repo and then install it in all those projects so that way you can stay up to date, so they can spread like these best practices all over their organization. So that would be like one way to do that, right?
Exactly. And you know, if it works in monorepos, it works in separated repos. It's a pretty general approach for you trying to do these things.
Definitely sounds amazing. So where did the original idea for the better actually came from? Like when did you sit down as like, okay, like I think I'm onto something?
Well, it basically happened when I moved company and saw exactly the same problems that I'd been seeing at a previous company. And it was actually specifically originally that button case of like having to migrate a ton of buttons and taking a long time to do it with a really long-lived branch that took forever to merge. And I figured there just had to be some less bad way to do it. Yeah, that was basically the original seed. Yeah.
Sounds about right. So what I seen like in your code examples was there was like a better file test, and that was like a class you have been importing from one of the packages. But then on the future slides, then you showed there was like a better ESLint, better TypeScript, better regex, and all this kind of stuff. So those are like two levels, right? One was the class, the other one was the packages. So can I assume that these other packages have some other classes which then express other kind of better tests? Is this
So
correct?
they're all better at file tests. So if you want to create your own, for example, like when I sat down to create the Angular test that I'm about to release, and I just used better file test.
All
So
right. Okay. So it's like
Angular is
implementations of the better file test, which then checks for some other stuff.
exactly. The better
Okay, that
file test
makes
is
sense.
just responsible for associating issues with a place in a file. And so
Right.
if those issues are lint issues or typos or anything, they just get attached that way.
Makes perfect sense. So can you maybe share with us like what was the most interesting test you have written in Better yet? Like what were you like looking for in your code base?
So I've had a couple particularly interesting ones that I've enjoyed looking through. The biggest one has been accessibility issues. So
Right.
a pretty common thing that I've again seen in companies is that it's quite difficult to often quite difficult to prioritize accessibility issues. And so having a test that more like an end-to-end test that spins up a site and runs some kind of audit, say with X, and presents you a list of all those issues, and then just trying to fix them one by one. That's a pretty interesting use case to me. Also, bundle size is another good one.
Right.
So you print out the size of all your bundles and try to not make them get bigger.
Definitely. Definitely. Another thing which comes to mind is like, so I've seen that like you can make the test fail. You can also, well, the test will fail by default if it makes stuff worse. And then you showed us that there is actually like this update flag where you can kind of force it so you are not blocked, because we never really want to block our colleagues, because if there is like some hot fix coming out or pressing issue, like it cannot be like that, oh yeah, we cannot fix this because it's not better, of course.
Exactly.
But then basically brings up the question, at least like in larger organizations, what tends to happen is that if something is not like forced, then people just like get to used to using that flag. So what is like your personal experience in the place where you already used this? Like what was the ratio? Did things tend to get like better over time, or it's more like stale, or what was your personal experience?
So again, it's definitely a cultural thing. So there is the update flag, but there's also a strict flag. And so the strict flag turns off anything that tells you about the update flag. So usually when the test fails, it says, hey, if you really need to, you can update this. But if you run it in strict mode, it doesn't tell you about that. And so if people don't know about it until they really need to know about it, that's a good way to encourage it.
That
I
sounds
think
like a pretty cool trade-off, actually. Like, okay, like there is a way, but you will take a bit of a digging to realize that there is a way. So
exactly.
it's just maybe easier just to fix the problem and not spend half an hour to figure out how to work around this. So that's a very cool approach, I have to say.
Yeah, and again, it's teams want their stuff to get better. You know,
Of
what
course.
what I think it is that prioritizing that stuff is really hard, and so
Yeah.
I think
And
this approach helps.
And yeah, definitely, because then you get something like visible, which you can say like, okay, like we kind of have to do that, right? So it's not just like it will take a bit longer maybe, but we actually have to do that because here is this output and we are really striving to make things better here. So it's maybe like a leverage where you can communicate like with your manager or like somebody like above you, like, look, the things are actually getting better and we have some explicit output how we can prove this. So I think that's always very good to enable
Exactly,
people to make this like more visible and more transparent. So it sounds like a win-win for everyone.
absolutely, and it's countable. It's people love numbers. If you can say,
Oh
hey,
yeah,
a
yeah,
month ago we had 500 and now we have 400, people like that.
definitely. No, sounds really amazing. And I actually going to try this out in our code base like next week, because it really sounds like something which may nudge the people in the right direction. So
So
thank you very much for sharing and all your efforts.
thank you.
So that being said, so if there are not any more, oh, do we have a question actually? So from Radovan, are there some recommended must-have tests which could be beneficial in general?
Good question. I would say probably no, because it kind of depends on the code base. The nice thing about this is that there's actually a pretty clear migration pattern, right? So you introduce something through Betterer, and then you complete the test, and then you just move that to a real part of your code base. It doesn't need to be part of Betterer anymore. It's just you've got to that state, and you move the config to your TypeScript config or your ESLint config or whatever it is. So it's very much on a case-by-case basis.
Makes sense. And then we have one more question from Lucas: how to handle merge conflicts in the better configuration file. So if people really want to make it better, I want to make it better fast so that they start stepping on each other's toes.
Yeah, I have to think about this a lot because again, a big code base. And it's something I have in the longer version of this talk, but skipped over. But there's actually a better merge command, and that will essentially do most of it for you. There's a whole workflow that I've got some docs about. Basically, you want to run it in pre-commit, you want to run it in CI, and then when you get you can basically set up Git to automatically merge this file when there are conflicts in it.
So it sounds like this case is also covered like by the tooling itself, which sounds amazing. Cool. So that were all of our questions. So then thank you very much, Greg. Hopefully to see you at the next edition of the Angularday and wish you all the best. Ciao,
Sounds great.
ciao.
Thanks, bye.